Okay, so let's start the today's tutorial. So in this tutorial, we will be covering 12.1, 12.2, and 12.3. Let me just share my screen. Okay, all right, is the screen coming through?
Are you sharing your screen?
Yes. Wait, just let me share.
Yeah, now I see it. Not anymore.
Right. Uh,
Yeah, I see it now. Yeah.
okay. All right. So let's start with exercise 12.1. So 12.1 is on page number 854 of your textbook. Let's take the first question from the exercise. So we have to find the value of these expressions first of all. So let's do part number A. So for part number A, we have so part number A. So we have 1.0 complement. So 0 complement is 1, which was 1.1. This is equals to 1. Okay. So we have 1 plus 1 complement. So 1 plus 1 complement is 0. So 1 plus 0 equals to 1. We have 0 complement. 0 complement is 1.0. So 1.0 equals to 0. D. So we have 1 plus 0. We take 1 plus 0 is 1. 1 complement equals 0. All right, so pretty straightforward. Yeah. Any question from this question? All right, no question. Let's move on to the next one. So we have here, we have to show that 1.1 plus 0.1 plus 1 equals to 1. Right, so we will have here so we have 1.1. So we have 1.1 plus 0. I'll just call C as the word for complement. We're taking 0.1 complement, and then we're taking plus 0. Okay, so 0.1 is basically the line over there. So I'm just writing it as C. Okay. All right. So this is equals to. So 1.1 is 1 plus complement 0.1. 0.1 is 0, 0 complement is 1. 1 plus 0. Okay. All right. So we have 1 plus 1 plus 1 plus 0 is 1. 1 plus 1 is 1. Okay. So hence proved. All right. Sounds good. Right, moving on to the question number 5 here. Okay, so we have to use a truth table to express the value of these Boolean functions. Okay, so we can take a table of let me insert a table. So 4 by 8. Let's do 4 by 8. Okay. So actually it should be 4 by 9. So it will have 4 columns and 9 rows. Okay. All right. Okay, so here we have, let's take part A. We have x, y, and z. So we have x, y, and then we have z. And then we have x complement. We have the complement of x. We'll just say complement x. And then we have y. Okay. So we have x 1, 1, 1, 1, then 0, 0, 0, 0. Okay. So we have 1, 1, 0, 0, 1, 1, 0, 0. Z is 1, 0, 1, 0, 1, 0, 1, 0. Okay, so we take the complement of x. So this is 1 becomes 0, and then y. Okay, 0 dot 1. Okay, so 0 dot 1 is 0. Okay, so we take complement. So 0 dot 1 again 0. 0 dot 0 equals to 0. Again 0, 0. So we have this 0 complement becomes 1, 1, 1 is 1. Same thing. 0 complement 1, 1 dot 0 is 0, 0. Okay. This for part A. Let's do part C. Table support by 9. Okay. So this is going to be part C. All right. So we have x, y, z, x, y, z, and then here we have x, and then we have the complement of y. I'll just put a dot here. That complement of y, and then we have plus x, y, z complement. So complement of x, y, and z. Okay. All right. So here we will say 1, 1, 1, 1, 0, 0, 0, 0. Okay. 1, 1, 0, 0, 1, 1, 0, 0. All right. We have 1, 0, 1, 0, 1, 0, 1, 0. All right. Here we have this x. We take the complement with y. So 1 dot 0, 1 dot 0 becomes 0. Now we have 0 plus x, y, z. So we x, y, z. So x dot y dot z, all are 1. So it becomes 1. 1 complement 0. So 1 plus is equals to 0. Right? So we have now 1, 1, 0. So x dot complement of y, this becomes 0. So this will make this 0 plus complement x, y, z, so x, y, z. So we have 1 dot 1 dot 0. So this becomes 0. 0 plus 1 equals to 1. Okay. Likewise, we will fill it up with the rest. So this will be 1. This will be 1, 1, 1, 1, and 1. Okay. Just using the same logic. Let's do one more here. D part. Okay, so we have x, y, and then we have z. Then we have x, and then we have y, z plus y complement of y, and then dot complement of z. Okay. All right. So 1, 1, 1, 1, 0, 0, 0, 0. we have here 1 1 0 0 1 1 0 0. All right. Okay. So this become 1 0 1 0 1 0 1 0. Okay. All right. So here we have yz. So y dot z, it's 1 plus complement of y, complement of y, complement of y, it's 0, dot complement of z is 0. Okay. So this becomes 1 into 1 plus 0 is 1. 1 dot 1 is equals to 1. Okay. So therefore this is 1. Okay. So we have yz 1 dot 0 0 plus complement of y. So y complement is 0 dot complement of z is 1. So this becomes 1 0 dot 1, it becomes 0 0 plus 0 0, 1 dot 0 equals to 0. Okay. Likewise, we will fill out the rest one. So this is 0, this is going to be 1, this is going to be 0 0 0 and 0. All right, any questions here? All right, no question. Let's move on to the next one. We have question number 13 here. So we have to show that x y complement plus yz complement plus x complement z equals to this on the right hand side. We can do this using the table as well. So we can have table here. We can have 11 by 9. All right. So we have x, y, z, and then we can have x dot complement of y, and then here we can have y dot complement of z. Here we have x complement dot z. Okay, and then we have x, this thing here, xy complement plus yz complement plus x complement z. Maybe I can copy paste this here. All right, let's resize this. Okay. Then we have x complement y, x complement y. Then we have y complement z, y complement z. Then we have x z complement. X dot complement z. And then we have this thing here. This one here. All right. Okay, so we have x complement y y complement, uh, y z complement, x complement z. We have this whole thing here. We have x, this is y dot x complement. We have y complement z, and then we have x z complement. Okay, sounds good. All right, so here we have 1 1 1 1 0 0 0 0, just filling out a typical truth table. 1 1 0 0. So we have 1 0 1 0 1 0 1 0. Okay. All right, so x dot y complement. So 1 dot 0 equals to 0. Okay. 1 dot 1 equals to 1, 1, sorry, 1 dot 0, because it's y complement. 1 dot 0 equals to 0, 1 dot 1 equals to 1, 1 dot 1 equals to 1, 0 dot 0 equals to 0, 0 dot 0 equals to 0, 0 dot 1 equals to 0, 0 dot 1 equals to 0. All right, so we have 0 0 1 1, and then the rest 0. Okay. All right, so we have y z complement. This will be 0 1 0 0 0, and then we have yeah, then we have 1 0 0. Right, so I had 0 1 0 1 0 0 0 1 0 0. Okay, we have here 0 0 0 0 0 1 0. Right, so based on the same logic, we will be filling out the rest ones. So now we have this one here plus this one plus this one. So 0 plus 0 plus 0 is 0. 0 plus 1 plus 1 is 1. So 1 plus 0 plus 0 is 1. 1 plus 0 plus 0 is 1. This is 1. This is 1. This is 1. And this is 0. Okay. Likewise, we will do the same thing here. So this will be 0 0 0 0. And we have 1 1 0 0. So we have 0 0 1 0 0 0 1 0. Now we have 0 1 0 1 0 0 0 0. All right, so we have to just add them together here. 0 0 0 0 plus 0 plus 0 is equals to 0. 0 plus 0 plus 1 equals to 1. This is 1, this is 1 1 1 1 and 0. Okay, so now that we see on the left hand side here, so this expression, it has these values, and this expression here, it has these values. Now we see that these values are exactly equal to each other, right? So therefore we can say that the left hand side equals to the right hand side. All right, any questions here? Okay, if no question, let's move on to the next one. So we have to basically verify the De Morgan's law. So in order to verify the De Morgan's law, we will once again use the truth table. Okay, so we'll have insert a table. Table 5 to 5. Okay. All right. So here in, okay, let's do x, y, we have xy, and then we take xy complement. Then we have complement of x, complement of y, then the complement of x plus complement of y, and then we have x plus y, then take the complement of the whole thing, x plus y, then we have the x dot complement y. Okay, that's good. Okay, so we have 1 1 0 0, we have 1 0 1 0. Okay, one, so we take the dot product, so 1 1 oops, 1 1 0 is 0, so 0 and 0. Okay, we take the complement of this, so it becomes 0 1 1 1. Okay, we have the complement of x, so it becomes 0 0 1 1. Complement of y, it becomes 0 1 0 1. Okay, so we add these together, so 0 plus 0 is 0, 0 plus 1 1 1 1. All right, we have x plus y, x plus y, 1 plus 1 1, 1 plus 1 0 plus 1, 0 plus 1 is 1, 0 plus 0 is 0. Okay, we take the complement of that, so it becomes 0 0 0, and then this becomes 1. Okay, now we have this complement of x, this one here, dot product this one. Okay, so 0 0 is 0, 0 1 is 0, 1 0 0, it's equals to 1. Okay, so this one here, we know that this complement x plus y equals to complement x, complement of x dot complement of y. Since the truth values matches each other, we can say that the left hand side equals to the right hand side. So left hand side equals to the right hand side. Okay, so we can say that this equals to this here, hence De Morgan's proved. All right. Any questions here? All right, if no question, let's move on to the next exercise. So this exercise is exercise 12.2. It's on page number 858 for textbook. Okay, so the question says find a Boolean product of the Boolean variable x, y, and z or their complements that has the value 1 if and only if x equals to y equals to 0 and z equals to 1. Okay. So we have to basically find a Boolean product with these values. Okay, so let's start again. So we have the complement of x dot complement of y dot z. Okay, so for example, if here we have x, y, 0 and z equals to 1, this should evaluate 1. So let's try that out. So we have complement of 0 dot complement of 0 dot 1 dot 1. Okay, so complement of 0 is 1 dot 1 dot 1 equals to 1. Okay, so therefore this will be the answer here. Let's do part B. We have x equals to 0, y equals to 1, and z equals to 0. We have to find such a Boolean product to which the answer evaluates to 1. Okay, so we have to basically find such a Boolean product. Okay, so this will x complement dot y dot complement of z. All right, basically wherever it's 0, we are taking its complement. All right, so we have complement of 0 dot 1 dot complement of 0. Okay, so 1 dot 1 dot 1 equals to 1. Okay, pretty straightforward, not any big logic. So here we have x only 0, so we will only take the complement of x. All right, so we will take complement of x dot y dot z, right? So we have complement x is 0 dot 1 dot 1. This is equals to 1 dot 1 dot 1 equals to 1, right? Last z. So we have x, y, z all 0. So we take the complement of all of them. X dot complement of y dot complement of z equals to complement of 0 and then dot 0 dot 0. This is equals to 1 dot 1 dot 1 equals to 1. Okay, pretty straightforward. Any questions here? All right, no questions. Let's move on to the next question. Question number 7. So previously we'd find a Boolean product. Now we have to find a Boolean sum. Okay. All right. So here we have in Boolean sum, basically we have to make sure that there is at least one in the statement, okay, in the expression. So here the first one, x equals to y equals to 1 and z equals to 0. All right. So here we can say x here we have to basically make sure that has the value 0. Okay, we don't have to check for the value 1. We have to check for the value 0. It's 0. Okay, so we have to make sure that there is all of them are basically equals to 0. Okay, all right. So here we'll take complement of x dot sorry, it's a part sum. So complement of x plus complement of y plus, and then we have the z, which is already 0, so we don't need to take the complement. So this will become complement of x 0 plus 0 plus 0. This is equals to 0. Now we have y, z, y, x, y, z are all equal to 0 here. Since it's already 0, right? So we don't need to do anything at all here. So x plus y, this is equal to 0 plus 0 plus 0. So this is basically a value is to 0 itself. We don't have to take the complement of anything at all, right? So the next one is x equals to z equals to 0, okay, and y equals to 1. Here we only need to take the complement of y to make sure that this evaluates to 0. Okay, so we have x plus z plus complement of y, which is equal to 0, 0 plus 0 plus 0, which is equal to 0. All right. Any questions? All right. If no questions, let's move on to the next one here. Okay, so we have here show that a complement equals to x. So this operator here, it's basically the NOR operator, right? So x nor x. Okay, so NOR basically it's just the complement itself. Okay, so what we will do is so we can basically add a table here to prove that. Insert a table of 3 columns and 3 rows. All right. Okay. So we have x, and then we have the complement of x, and then we have x, and then all can just say nor. So we can say nor, or we can just put this operator, the downward arrow. Right. So 1, 0. The complement will be 0, 1, and then x nor x. So if you know the truth table of the NOR, then you will know that 1 dot 0, 1 NOR 0 is 0, and then we have 1, 0, 1 is 1. Okay, so basically the left hand side equals the right hand side. This is part A. Part A. This is part B. All right, okay. So we have x, y. We have x, y equals to x nor y nor y. Okay, so x, y. We have x, y, and then we have x nor x, x nor x. Have y nor y. And then we have x nor x. Then you can say nor. You can say y nor y. Just a little bit. Okay, maybe I can reduce the font size here. Right, this sounds good. So 1, 1, 0, 0. We have 1, 0, 1, 0. X dot y 1, 1, 0, 0, 0. X nor y. So this will be 0, 0, 1, 1. Basically, it is basically nor is basically just like taking the complement. Okay, so y nor y, taking the complement of y itself. Okay, so this becomes 0, 1, 0, 1. Okay, now we have this, and then we have this. The 0 nor 0 is 1. Okay, 0, 1 is 0, 0, and 0. Okay, so we have the xy here, this one here, this is equal to this right hand side here. So we say that the left hand side equals to the right hand side. Okay, let me say hence proved. All right, any question here? There's no question. Let's move on to question number 19. So we have to show that the set of operators plus and dot is not functionally complete. So basically it is impossible to represent the complement of x, for example, using plus and dot, right? because there is no way to get the value of 0 if the input is 1, right? So we cannot basically use the plus and dot sign to revert the value, take the complement of the value. So therefore, they're not functionally complete. Okay, so we also needed the complement operator. Okay, all right, let's move on to the next exercise. So basically, this is around the logical gates. So this is exercise 12.3. It's available on page number 863 of the textbook. Let's take the first question here. So we have to find the output of the given circuit. So here, this circuit here, this one here basically represent the OR, this represents the and this represents the inverter. This is the inverter, right? Just basically like taking the a complement. All right. So we have this, we have X and then Y. These are OR together. So X plus Y, okay? X plus Y, and then X plus Y. This is the AND operator, right? So we put the dot. This is AND with this Y complement, all right? So complement of Y. All right, so the result will be basically the result of this expression. Question 3. Question 3, okay. So we have X, Y, this one is AND, so X dot Y, right? And then over here, they're OR together, right? So I'll just, they are taking the inverse, so the complement of this, right? And then we have the OR operator here, which basically is plus. We have Z complement of Z, right? Complement of Z OR together plus with X, okay? Plus X, right? So this is the result. So we have this one here is basically represented by the left node of this gate or the circuit here. So this from here to this part here is basically this complement of XY. And this side here, right side, is basically on the plus hand side of this, which are basically the both sides are OR together or plus. This plus represents the summation. Right, let's take the last one. So we have question number 5. This is here we have 3 nodes, X, Y, Z. X, Y, Z. So X, this is OR operator. X plus Y plus Z. All right. So X plus Y plus Z. We know that this is an OR operator, so we will just put the plus sign here, and then we'll take this side here. Okay. So X complement, we're taking the complement of X. So this will be the complement of X. This is OR operator or gate. YZ, Y plus Z. Now we have plus here because it's going here. Now we take this side of the gate. All right. We see that all X, Y, Z are, we are taking the complement. So we say X complement of X plus complement of Y, Y plus complement of Z. All right. So this is the output of this gate. Right? Any questions here? All right, if no question, let's move on to the next one. So here we have use NAND gates to construct circuits with these outputs. Okay, so we have to use the NAND gate to construct the output of these circuits. Okay, so we will be drawing circuit, but I have already got the for you. So here, just I'm gonna put it on to the next one. All right. So here, part A. So x complement, here we have x and then we have the x as well. So we NAND it together. So this is the symbol of the NAND operator. So if we take x NAND x, so this is basically equals to x complement. Okay. So we use the NAND operator to basically take the complement of this. We can have also done it using this operator, NOR operator, but because the question asks us to use the NAND operator, so therefore we have to use the NAND operator. Okay. Question B, x plus y here. So x plus y here, we have x, we NAND it together, which will give us x complement, and then we have this y NAND, right? This will give us y complement. So we have x complement, and then we have the y complement, right? So we NAND that together, so this will give us x plus y. Right? So we have, let's say part C. So we xy, we have to find the dot product xy here. So using the NAND gate. Okay, so we have xy, we take the dot, the NAND of x and y. So this becomes x NAND y, and same thing x NAND y. Okay, and then we apply the NAND gate once more to get xy. All right, so basically if we want to get the summation or the plus, then we have to NAND the same values together. And but if we want to get like a dot product of them, then we have to basically take the different x and y variables to NAND them together to get the xy. All right, any questions here? All right, so if no more questions here, then this will be the end of this tutorial. So in this tutorial, we covered 12.1, 12.2, and 12.3. And I hope to see you guys in the next tutorial. Okay, take care and bye now.